Hello everyone, it is April 13th, 2022. This is Geo-Rant 161, and this is basically what I'm going to be talking about today, and some misnomers that even geologists use. But first, I just need to talk about columnar jointing in general. I've done extensive videos on this. I will link those below. I've done extensive videos on Devil's Tower, link below, as long as any relevant stuff you're going to see here, because I do these in one straight take, unedited. Let's talk about Devil's Tower, Wyoming. For those of you that don't know, maybe you've seen Close Encounters of the Third Kind, the mashed potatoes thing he makes. That's Devil's Tower. Yes, it's a real place. Yes, it exists in Wyoming. No, there's no apostrophe there, but that's a story for a different time. It's about 265 meters in height, and each one of these columnar joints are about 10 feet wide, 3 meters, and they can be nearly this long. As you come down, the columnar joints change direction and disappear. Talks for other times. But columnar jointing, it's a type of fracture pattern. Rocks fracture all the time, and they form a lot of times different patterns. This is the one that's hexagonal on top. They can form squares on top. They can form trapezoid looking things on top, even triangles from time to time. But columnar jointing is special because of the way it forms. And there's plenty of examples of this in the world. Columnar joints are suspected to form from cooling lava, either surface or, I don't want to say underground, because from cooling melt that melts quickly. And they form generally perpendicular to that flow. So if our lava was this way, it would be this way. Now you may be like, wait, that's a weird shape. But yeah, like I said, link below. Okay, we're not going to go down rabbit holes here. But I will often hear even fellow geologists say, columnar jointing forms in basalt. Does it? Oh yeah, most of the time. And like I said, Ireland is examples of this. Isle Royale and the Upper Peninsula is examples of this, and many other places on Earth, but it doesn't have to. As a matter of fact, this isn't basalt, and I've heard geologists say it is. It is not. It's also not a tree stump, but I've beat that horse before too. This cooled from a melt, okay? From, melted rock. Now, you may see I have, why do you have this QAPF diagram, Stephenson diagram, or the IUGS diagram on here? And I'm just going to talk about it here and how because you need to know this to know why we call rocks certain rocks. All right, just so you know here, let's do this really quick. My plutonic or phaneritic, these are kind of interpretive, so we're getting away from them. So phaneritic is written in this bluish green. Aphanitic is written in orange. Phaneritic is coarse crystalline rock, like your granites, stuff like that. Aphanitic is fine crystalline, like your basalts and things like that. And I just put some of them here. Now this is based on percentages, this diagram here. And it is divided further than this and has specific lines with certain percentages, but I couldn't fit it all on here, so I simplified it so you get the general feel. Now, why am I bringing you into this? Because I need to tell you about something here. It's QAPF, quartz alkali feldspar, also known as K-spar, plagioclase, feldspathoid voids. Real quick about this chart. This line between the A and the P is always 0, always. That's its numerical value. Here's 100% voids. Here's 100% quartz. You're almost never going to see rocks here, so I didn't even bother putting those types on here. Now, this is not like the USDA textural diagram. You are plotting 3 things, but you're not just plotting 3 lines. You have to normalize twice. When we plot on here, this is for felsic to mafic rocks, not ultramafic rocks or ash flows and igneous rocks. Those have their own classification systems. But anyway, alkali, this side here means 100% K-spar, 0% plagioclase. This is 100% plagioclase, 0% K-spar. So these kind of swing back and forth like a pendulum in these percents down here. But you always, so that's why you plot, you remove your You remove most of your coarse-grained stuff first. You pull it out. When I say coarse-grained, I mean like in a granite, if you have mafics in there, you pull those out. Obviously in a basalt, you do that as well in this classification system. So you pull out your mafic minerals, and that's your first normalization. Then you plot that as a line up or down, and then you got to normalize again for these two, and that's your pendulum. You may be like, what's this, Steve? Why is this down here? Why isn't this like a fourth part? Why isn't this a square? Well, because feldspathoids or foids cannot physically form with quartz from a melt. It's chemically impossible to form together. Okay, if you form quartz, you're not going to form foids. If you form foids, you're not going to form quartz. So if you have no quartz in your rock, you use this part of the diagram. Okay, use the fat part instead of the cap part. Okay, most rocks, and geology classes, even up until 200 level classes, you'll be dealing with mostly this. This is rarely dealt with. It's commonly dealt with in places like the Coldwell complex of the Upper Peninsula, what used to be called Gardar, Greenland, where we're going in August, and this here. This is not a basalt, okay? We plot this, and I've done this. It plots over here. It's aphanitic, fine crystalline. Oops, sorry, I poked at it there. That's XLN means crystalline. So it's a phonolite. Well, it does have phenocrysts in it, but phenocrysts aren't coarse crystal. They don't define the rock. If you have more fine crystalline, you go with the aphanitic. You don't go with this. There are phenocrysts in there, okay, but it is a phonolite. Basalt's over here. Now, you can have basalt cross this line depending on who you're talking to. It may, but the point is, nothing here plots over here. It all plots over here, okay? So right there, columnar joints can form in non-basaltic rocks. People should really say mafic when they say that. But anyway, there's something else here I think is kind of funny, cool, and that I actually didn't find out until probably about 10 years ago. Joints are a fracture pattern. They're a brittle failure pattern without movement. If you get movement, you get a fault. Okay, so it's brittle failure, and it likes to form patterns. So, does columnar jointing only happen in basaltic rock? No, we just learned it doesn't. But does it only happen in igneous rock? There will be geologists who argue with you that yes, it does, but they're unaware of something. Like I said, it's a fracture pattern. It's a rock failure pattern. It has less to do with the composition than it does your directed heat source. You can get columnar jointing in sandstone. Paraguay, there's columnar jointed sandstones there. You're like, whoa, Steve, you just said it forms perpendicular to the flow of a melt. Yeah, it does. But what's important there isn't so much the fact that the rock's molten, is that you've introduced a high temperature source. And you can introduce high temperature sources without melting. You can do that through hydrothermal activity. You get hot water through some sort of intrusion deep down. The intrusion doesn't come up, but what does is the water, and it comes into contact with that geologic unit. And if it cools really quickly, heated fast, cools very fast, you can get columnar jointing regardless of the rock type. So before I rant along too much on this, I just want you to see that one other thing. You notice I have foid cyanite. When you name this, you wouldn't name it a foid cyanite. You'd put the foid in there. Nepheline, sodalite are two common foids. So you'd have a nepheline cyanite. That's just the placeholder. But you notice that they're right next to something. There are some trachytes. Now, even though I said these two cannot form together, okay, and in the same intrusion, they won't, but you can get two different intrusions in the same body. Does that make sense? Like, stocks and bathyllus might actually be made of multiple intrusions, so one might have quartz, one might not. And that's a key way to discern whether or not you have one or more magma bodies that cooled. Anyway, talks for other times. But You can see phonolites are similar to these. These are similar to these. Basically, rhyolite is the fine-grained version of a granite. It's the fine, sorry, I say grain, I mean crystalline in this case. So rhyolite is basically fine crystalline granite. Chemically, compositionally, mineralogically, I stumbled there, these two are the same, all right? Cyanites and trachytes. We have basalts and andesites with gabbros. Andesites, by the way, will never contain voids. Basalts can, depending on who you ask, all right? Tonalites and granodiorites are the coarse crystalline phaneritic version of a dacite. Okay, so that's why we use two charts. And these things are chemically, mineralogically identical to these things here. Now on the fine aphanitic part, these divisions are less drastic. They take up more area, there's less of them. And the reason for that is because on a phaneritic piece of rock in your hand, the crystals are big, and you can sometimes, with a hand lens you look, but even sometimes they're big enough, they're called pegmatites. They're big enough to identify without a hand lens. You can just look at it, but you can look at your hand lens, you can get a more detailed mineralogy in the field than you with a phaneritic rock than you can an aphanitic rock. So that's why the phaneritic part is more detailed and has more solid percentages than the aphanitic part. I think that's it. Something I want to mention too, just real quick and I'm done, I swear. I've gotten in arguments with people about rhyolites. I will call anything a rhyolite. Technically, some people think a rhyolite has to be a superficial lava flow. I don't see the point of that. We have been getting, for the past 30 years, trying to get away from that interpretive type of thing. And if you saw a chunk of rhyolite in a box on a test, and you called it a rhyolite, you wouldn't be wrong. You have no way to determine where it came from, its origin. A lot of people will call rhyolites felsites, but it's the same bloody thing mineralogically. It's just the interpretation is different. Felsites are underground, rhyolites are above ground. Yes, you can have aphanitic rocks cool underground, but I don't see the point of that. And most geologists are getting away from that. A rhyolite in a box is a rhyolite in the box, in the field, whatever, all right? So that's another reason why we're getting away from these and favoring these. Okay, and I think I've beaten this horse long enough. That's it. If you have any questions or comments, please leave them below, and I hope you learned something. Thank you.